Now that you have looked at the underlying philosophy behind hypothesis testing, I will remind you of it a little, and then we will move into the 6-step plan for completing a hypothesis test. And then I will do a sample problem to help you master this 6-step plan. Hypothesis testing is based on this picture. Do you remember it? In the picture, we have a population. We don't know the mean, the standard deviation. But what we do is take a random sample. From the random sample, we collect the mean of the sample, the number in the sample we know in the standard deviation. We know that the mean of the population is clustered around the mean of the population at a given confidence level, and we can then calculate that confidence interval. We assume that S, the standard deviation of the population, is a good predictor of sigma, the standard deviation of the population. So the standard deviation of the sample is used to predict the standard deviation of the population. Hypothesis testing is about testing a claim to see if that claim is likely to be true or false. Now, I will point out to you, statisticians never say that it's true. We just fail to reject it. Or if it's false, we reject their claim. The only way to be absolutely certain is to evaluate the entire population. Hypothesis testing allows us to take a sample and make predictions about the population. That's what we're doing with hypothesis testing. Again, we're taking a sample and making a prediction about the population. Now, we have a 6-step plan to conduct a hypothesis test, and these 6 steps are very important. They're going to sound like they're Greek to you for just a little while, but I think you will see as we proceed that they make good sense. The first thing you do is state the null hypothesis. You state the alternate hypothesis. You establish the critical value. You find the test statistic. You draw your conclusions, and you write your findings into statements. So you have a plan, 6 steps. Now all you have to do is learn to do each of those 6 steps, and you will be able to move this. State the null hypothesis, the alternate hypothesis, establish the critical value. That's going to be based on your confidence level. Find your test statistic, draw your conclusions, and write your findings into statements. Now, once you learn to do these 6 steps, you can utilize the hypothesis testing process to evaluate claims based on sampling techniques and utilization of the central limit theorem. This becomes a very neat process for testing a claim made by anyone. Now, step 1, state the null hypothesis. The null hypothesis is the claim being made. The manufacturer says that the average mile per gallon of this vehicle is 34. The average lifetime of this light bulb is 1,100 hours. The null hypothesis is the claim being made. It is always that mu equals a set value. It is written as follows. For step 1, H naught, or H, the null hypothesis, is that mu equals a value claim. This is a very easy step. You read the problem. What are they claiming the mean is? You write the null hypothesis. Then the null hypothesis, what we're going to do is that we're going to have an interval, and we claim that mu is going to be in this interval. It's not going to be outside the boundaries. It will be within the boundaries if H naught, or the null hypothesis, is true. Notice we call it H naught for the null hypothesis, and the alternate hypothesis is HA. Okay, so H naught and HA. We might say we're 95% confident that mu is in this interval. Now, I want you to envision what has happened here. The manufacturer has made a claim. Based on that claim, we have taken a sample. The sample has X bar. We have built a 95% confidence interval around X bar, and what we're going to do is look to see if mu is in that interval or if it is not in that interval. Now, the alternate hypothesis is what is expected if the null hypothesis is false. Now, I don't want you to miss the fact that we have 2 possibilities. We have the possibility of the null hypothesis, that mu equals a value, and then the alternate hypothesis is that mu is not that value, and it can be expressed in 3 forms. The first form is mu just is not that value, doesn't equal it. That means that we have error on each end, and I'll show you that in a minute. Mu might be greater than that value. Suppose you're going to move your furniture from Dubai to San Antonio, and they give you the average cost. Well, if the cost is lower than that, you're not worried. But if the cost is more than that, then you get worried, okay? So the other one is that mu is less than a value. Suppose you buy a car and they claim it gets 34 miles per gallon, and you find out that your vehicle gets less than that, then you're worried. So 3 possibilities driven by the type of problem you have. Mu is not equal to a value, mu is greater than a value, mu is less than a value. The most common alternate hypotheses are mu is greater than a value or mu is less than a value. So generally what happens in H0 is they claim that mu is a value. And then you're going to look at it and say, well, it's not equal to that, it's greater than that, or it's less than that. Now, which of these do you use? Well, that's determined by the problem. And you have to be clever, you have to read the problem, and use your good judgment and common sense to determine which alternate hypothesis fits. Now, the decision is driven by the problem and affects the remainder of the hypothesis test. You have to get the alternate hypothesis correct. The null hypothesis is very easy. The alternate hypothesis comes from the framing of the problem, and based on which of these 3 it is, then your critical value in step 3 is going to change. I'm going to show you each of these. If mu is not equal to a value, then you have error on each end. It could be too big or too small, and that error is alpha over 2. For instance, if you're 95% confident, then alpha is 5%, and if it's a not equal a value, then you have 2.5% on each end. Now, this is called a two-tailed test because alpha is equally split on each side. If mu is less than a value claimed, then, and that's what you want to do, and you have 95%, then you have a full 5% error on this side. So if you draw the picture, you label the boundary, it makes it easier to understand what you're going to do from that day forward. This is called a one-tailed test because all the error is on one end. And if mu is greater than a value, is your alternate hypothesis, then same thing before. This becomes a one-tailed test. If you're 95% confident, then 5% of your error is on this end. This is called a one-tailed test because alpha is on one side only. Now, the critical value, Z critical value, is the Z-score that captures the confidence level of your problem, and it depends on your decision to do a two-tailed or a one-tailed test. If you're using a 95% confidence, you have 5% error, and if you have 2.5 on each side, then your Z critical value becomes plus or minus 1.96. We did that in our confidence intervals before. If your mu is less than a value claimed, your alternate hypothesis is that mu is less than a value, your 5% error is trapped down here, and your boundary becomes negative 1.645, becomes your critical value. And if mu is greater than that at a 95% confidence error, then a confidence interval, then your error is 5%, and it is all trapped here, and your Z confidence value or critical value becomes 1.645. Now, I want to show you that again. 5% is on a two-tail, not equal to an alternate hypothesis that it's not equal, 2.5% on each side. You have 2.5 on each side is captured by negative 1.96 and positive 1.6. If its mu is less than a value, then your Z critical value is negative 1.645. And if its mu is greater than a value, it's 1.645. Now let me give you some guidance here. When you do your alternate hypothesis and you select which of these it is, draw the picture. Label label in that picture what the boundary is. And if you draw a mu not equal to, put the arrow on both ends. If you draw a mu less than, put the arrow on the left side. If you have mu greater than, put the arrow on the right side. That picture will help you substantially to label the correct z-critical value, and will also help you in the decision that you make. This is called a one-tail test when mu is greater than, mu is less than, or a two-tail test if mu is just simply not equal to. Now, the z-critical value is the z-score that captures the confidence level of your problem. If you're 95% confident, two-tail test, it's going to be negative 1.96 and positive 1.96. If you're 95% confidence and it's a one-tail test that it's less than, it's going to be negative 1.645. If you're one-tail test at 95% and it's greater, mu is greater than that value, it's going to be 1.645. The z-critical value depends on your decision to do a two-tailed or a one-tailed test. And the decision to do a two-tailed or one-tailed test is driven by the problem. The critical value, here it is for 95% two-tailed, 95% one-tailed, 95% one-tailed. You see how the picture helps you interpret where the boundary is? If you take shortcuts and you don't draw the picture, then you're going to get lost. Drawing the picture will clarify the problem for you and make it easy to establish your boundaries. In step 4, you calculate the test statistic, and z-test is equal to the x-bar value, the sample mean, minus the claimed mean, the claimed mean of the population, divided by s over the square root of n. Z-test lets us know the z-score of the mu in the x-bar distribution. What z-score does the mu have? Really easy to calculate that. You plug in, you simplify. The first thing you do is take the square root of n. You divide s by the square root of n, x-bar minus mu. Then you divide this value by that value, and you get a z-test statistic. Your conclusion. Does the z-test fall inside or outside the rejection region? That's why your picture is so important. If your z-test falls outside the region, you reject H0. And if you reject H0, then you in fact have established HA. That's mathematical logic. If the z-test falls inside the region, then you fail to reject H0. So, it's really not hard. You either outside the region, acceptable region in the rejection zone, you reject H0. And if you're inside the region, then you fail to reject H0. Two conclusions, reject H0 or fail to reject H0. Then you need to put this into a final statement. Think about you're a statistician for a company and your boss asks you, well, what did you find with your sample? You said, well, failed to reject H0. Your boss hadn't got a clue. You have to put it in words. The evidence indicates that the manufacturer's claim is, and if you fail to reject H0, the manufacturer's claim is upheld. So, or if the manufacturer's claim is rejected, if you rejected H0, is not true. So, you've got a 6-step plan. You state the null hypothesis, H0, mu equals. You state the alternate hypothesis, HA, mu is not equal, less than, or greater than. Establish the critical value. That's based on your confidence level. If your confidence level is 90% or 95% or 98%, you have to draw the picture and label the z-score that works. And find the test statistics. That's x-bar minus mu divided by s over the square root of n. Look at where it lists and draw your conclusion. Your conclusion will either be reject H0 or fail to reject H0. And then you put it into words. Now, you're making good headway. I want you to keep the faith. In just a moment, I'll add the video where we go through and we actually work a problem. And working the problem should make it very clear to you because these are skills you've already learned. You're just applying them. So I wish you the best. You've got this. You're going to get up the ladder.